So, we start a new topic. As you have seen, the topic is evolution of networks. So, before really starting, I would give you some examples. I think I have shown you these examples, but we will just revisit these examples. So, this is a network of business ties in US biotech industry, okay, and you see very complex networks emerging, okay, where there are investment, pharma, research lab, public undertakings, financial links, R&D collaborations, etc., making it a heterogeneous complex networks. Okay. Take this example. So, this is the internet, okay, the routers, how the routers behave, and for strong router you have a bigger flash, and for weak router you have a smaller flash. Okay. So, this is the collaboration network of scientists who do network research. Okay. See this, I think I have shown you this again previously also. So, this is the 9/11 terrorist network. Okay. So, you have this, the terrorists, there are 5, you can see there are 5, oh. Okay. Sorry. Okay. So, there are 5 5 different types of dots. 4 are the 4 planes which attacked, and the 5th is other associates of the hijackers. So, you have again a complex net, who talked with whom. Okay. So, this is the genetic interaction networks, where you have different polarity, cell wall momentum, different types of nodes, and accordingly you have interactions with similar type or different types, and this gives a entire complex networks. Okay. This is yeast protein interaction network. Okay. So, in a yeast, how proteins interact, okay. This is, I think we showed you, this is the left side is the road network, while the right side is a airlines network, and what we see that the airlines network follows a power law. I think we talked about it, power law. Power law means what? If you take in log, you actually get a straight line. We will come to the exact point, but if you take a log and plot the degree distribution, then you will get a straight line. Okay. In common words, what is power law? Most have smaller degree, only few have higher degree. In a very layman's term, most have smaller degree, only a few have higher degrees. Okay. Okay. So, this is the Swedish sex web. I think again you have seen that who has gone out in a date with whom. Okay. 2 types of nodes are there, females and males, and again you see when we plot the degree distribution for males and females, you get 2 power laws. Okay. So, the question is very important. Question is that most of the real life network actually follows power law. So, this you can see this this type of networks. See this, what happens is, you see this is the World Wide Web, the degree distribution of the World Wide Web. This is the degree distribution of co-authorship networks. This is the degree distribution of power grid of Western United States and Canada. Okay. So, which power grid has how many transmission lines. Okay. And this is again a very obscure data, but social network of 43 Mormons in Utah. Okay. So, this is a Indian tribe, a collection of tribe, and who networks with whom, that is given. So, most of this actually from the point in showing this 4 types of network is, these 4 types of networks are actually extremely diverse and really do not have relationship with each other, but all these networks and many others like this begins to show power law. Okay. So, the natural question comes is, how do power law degree distribution arises? So, am I able to drive forward the question that how is power law degree distribution arises? This is a very interesting, means what we are saying, that in most of the natural systems is power law is arising. So, why do power law arise? This is the question which we want to ask. So, in order to answer this question, what can be done? What will be the technique? The technique will be basically doing some modeling. Okay. So, actually the technique will be basically doing some modeling. What is the modeling? What is the modeling about? If we see this, we have a network, okay, and at each step a new node will be added to the network. So, what is happening? The model will assume that you have a network, and at each step a new node is added to the network. So, each node will come with some new edges. Okay. So, this is clear that they have a static network, and at each step some new node is coming with some new edges. Now, the question which we want to ask is, how are the new edges getting attached? Okay. This is the basic question which we can ask, how are the new edges getting attached? Clear? Am I clear? Okay. So, how can the new edges get attached to old nodes? Tell me one possibility. Randomly. So, for each individual edge I pick up a random node and attach it. For this I attach this, for this I attach this. Okay. So, this is a possibility. Am I clear? So, this is a possibility. What are the other possibilities? Okay. So, what is the other possibilities? Add to nodes which are more popular. Okay. So, add to nodes which are more popular. Okay. Shomik, tell what is your favorite destination for holidays? Huh? Okay. Nirav? Akshit? Okay. San Jagan. Hey, this is not fair. Okay, so I put something. Okay, so what happens is immediately when you begin to see people's uh, people's choice, you begin to see that people mostly choose popular. So one which is already popular, that is chosen much easily. Okay. Because information means it's natural that you have a lot of information of Goa, okay, but you may not have information of Kodaikanal. Okay. So that's why you tend to choose Goa. Okay. So this feature is more popularly called as. So what happens? What happens in the end? That a huge lot of people land up in Goa, while very few people land up in Kodaikanal. Okay. So it's a avalanche effect. What we can say, it's a avalanche effect, that lots of people begin to go to Goa, while very few go to Kodaikanal. Okay. So this is more popularly known as rich gets richer. Okay. No, assortativity and this is different. What is assortativity? Assortativity is rich goes with rich, but here it is rich gets richer. Okay. So you can have a jamindar who is having relationship with lots of just peasants. So he is not going with really rich people, but he gets richer. Okay. So these two features are not really same. So this is understood that rich gets richer. Now, if I understand the basic qualitative concept, then okay. Now let us agree that okay, we have understood that rich gets richer. This is the normal feature, and this would generally tend to some people having lot of riches, while most of the people having no riches. Okay. This is clear, but why power law? It could be like a bimodal distribution. Am I clear that there can be two step, that some have huge riches, other have small riches. So it can be a bimodal distribution. So this is rich or money. Okay. So most of them are poor and some has huge rich. But essentially what we are seeing, we see something like this. Okay. So the question is clear. Although we can understand qualitatively that there will be unevenness and some will become rich, other will become less, but exactly power law is not clear to us. Okay. So this first was actually, if you think historically, actually this question led to the emergence of the complex network subject. Okay. So this is the primary question which basically opened the floodgate of all the other questions. Okay. Why we are observing power law in all the networks. Okay. So actually so there was a paper by Barbasi and Albert, I think in 2000, or I'm not, I think it's 1998. Okay. There was a paper by Barbasi Albert where they showed that due to preferential attachment, or what we say what we have said about rich gets richer, that was again coined in a different terms, preferential attachment, and due to preferential attachment actually this feature comes. Okay. So, then people took a lot of interest, and then people found that this has been discussed a long time back in actually 1965, okay, by Price, or it is Derek de Sola Price, and he talked in a different lingo. He talked about cumulative advantages. And he dealt with citation network, okay. And he showed that in a citation network power law emerges due to certain cumulative advantage. So, we begin to we tend to cite those papers which are well known. Okay. So, this is a figure which I can show is citation network of articles of perturbation of ion storms from 54 to 70. Okay. So, what we see is that this first article is cited by many, then it goes on. Okay. So, this is simplistic, it is not simplistic. Actually, we see that the first article which was first published in 1954 is cited by many. The second was in 61, that is also cited. The third is not cited much, the fourth is not cited much, but the fifth is cited again. So, it's do not think that it linearly follows the year of publication. Okay. There can be some relation, most of the time there is not. Okay. So, this is again seen that if you see in a physics domain, it takes say 2-3 years before you get cited. Okay. But in a computer science domain, you may be getting cited immediately. Okay. And the citation curve may fall very fast. Okay. That you are cited for 2-3 years, and immediately after that your work loses relevance and you are no more cited. While in physics domain, it may start a little late and it may continue along. Okay. That normally happens in a science domain vis-a-vis a engineering domain. Anyway, so that is not the question. The question is that, let us think. So, citation network is basically a directed graph. With nodes having in degree and out degree. Am I clear? So, with nodes having in degree, out degree. So, when a new node comes, it brings with it some out degree. Okay. When a new node comes, it brings with some out degree, which gets attached to nodes who already may be having some in degree. Okay. Who already may be having some in degree. So, now let us think that what will be the, if in degree already is k, then say probability of attachment AKI, right, is proportional to K. Okay. So, I am just trying to make it more formalized. I am trying to formalize it, that I have a node whose in degree is already K, then what will be the probability that you will attach to the nest is proportional to its degree K. Okay. And so how many, so if I think I am writing A all K's, that will be proportional to then KPK. Okay. So, what KPK shows? KPK shows that the probability of attaching an edge to a node with degree K. Okay. And so, if I try to normalize it, then it would be summation KPK. Okay. Am I clear? Okay. So, now question is, if I think of the citation networks, okay. So, what will happen initially? Nobody has any citation. Initially, nobody has any citation. So, in degree is equal to 0. So, if I take just K, then in degree will never come, because all in degree is 0. So, it will never pick up. So, then I have to have a offset. So, I have a offset, say K0 Pk summation of K plus K0 Pk. Okay. 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 So, now I write it again. So, K plus K0 Pk summation of K plus K0 Pk. So, this, let us, for simplicity, let us assume K0 is equal to 1. Okay. We can have any offset. I am just, for simplicity, we will later generalize it, but for the time being, let us think K0 is equal to 1. So, then this becomes K plus 1 Pk and summation of K plus 1 Pk. Okay. Am I clear? Okay. So, what is, so this node is coming, each node will come with some in degree, each node will come with some in degree. Okay. Let us, for simplicity's sake, think that this is constant and m. Yeah, each node will come with some out degree. I am sorry, each node will come with some out degree, means at the end of each paper you will have some citations. Okay. And let us, for simplicity's sake, think that each paper is having just m citations. We can vary m, it does not really matter, but for simplicity's sake we think that m is constant. Okay. Then what does this become? Tell me. K plus 1 Pk summation K Pk plus summation Pk. Okay. So, this becomes, top is okay, K plus 1 Pk, and down becomes, what is K Pk? K Pk is average degree is m, because each time you are coming with m in degree. So, average degree will be m. Okay. M plus 1. Summation of K Pk is m plus 1. Okay. Very good. So, now this is clear. Okay. Now, let us think in terms of a node. Okay. So, think this node at time t. Okay. So, I will try to, okay, I would make it a little more easier. So, what happened is you have a node, at each time a new node is coming. Okay. So, at time t, how many nodes will be there in the network? At each time one node is coming. So, at time t, how many nodes will be there at the network? T nodes. So, that is t is equal to n. Okay. I say if at time t n nodes are there, then n is equal to t. So, instead of t, let me use n. Okay. So, that I get independent of time and I just play with n. Okay. So, now let us see this again. So, if in degree already, so what does already means? It is p, k, comma n. So, the degree, the probability that node is of degree k at time n. Okay. Because I do not know, the question is I do not, what am I trying to find? What is my observation? Tell me what is my observation. My observation is, in spite of these nodes coming in, going out, there is some stable behavior at the end. All these networks, World Wide Web or collaboration or what the third one, power grid, all these networks are still growing. It is not that it has stopped growing. We have just stopped at one position and saw that it is behaving power law. If we take the data 5 years back or 5 years in the future, we will see the same thing is coming. So, what is happening basically? So, basically if I think pkn is actually equal to is actually equal to, if it is asymptotically, I am using a more mathematical term, if it is asymptotically stable, okay, then pkn is equal to, yeah, very good, it is independent of n. So, it is equal to pkn plus 1, it is pkn plus 2, okay, and shows that it should be equal to pk. Okay. So, this is the observation. Remember, the observation is that pkn, it slowly becomes independent of n, it is independent of n. But first, let us do the first step first. Let us think that only pkn. Okay. So, at pkn, how many nodes are there of k degrees? N into pkn. Okay. How many nodes are there? N into pkn. So, when I have a new node, then I will have a pkn plus 1. This two are not same. I will have a pkn plus 1. So, how many nodes will be of pkn plus 1? N plus 1 into pk. Okay. So, what does this show? Tell me. So, with this new node coming, number of new nodes which has been added in the k degree bin. Okay. In the k degree bin, you had say 10 k degree nodes, now you have 12. You can have 8 also. I am not telling that it has to be always increasing. You can have 8, you can have 10. How can this happen? Tell me, with these edges. See, this edge, if I have a k plus k minus 1 degree node, that gets a edge. Then what happens if I have a k minus 1 degree node and that gets an edge, that becomes a k degree node. Okay. So, that is an addition. Will there be any subtraction? If I had a k degree node and an edge is added to it, that will be subtracted. So, then what we have to do? we have to take the addition into consideration minus the subtraction into consideration. Am I clear? So, you have to take the, so in order to match this part, you have to take the addition into consideration and the subtraction into consideration. Is it okay? Okay, very good. So, how much is added? So, let us think if there was a k minus 1 degree node, if there was a k minus 1 degree node, so that was p k minus 1 comma n. Okay. So, according to this formula, or later this formula, how many nodes will, how many k minus 1 degree nodes will get edges? This number? No, not n minus 1. What we said, again come back. So this formalism is clear to you. So, let us come back to our old discussion. What we were saying, that if we have a k degree node, it is proportional to k, and all k degree nodes, if I take all k degree nodes, then what is the proportion? This k p k summation of k p k by summation of k p k, or we have later. So, what does this show? This shows that all k degree nodes, what is the probability that all k degree nodes will jump to k plus 1 degree node. Okay. All k degree nodes will jump to k plus 1 degree node. Okay. Okay. So, if one edge is added, if just one edge, but if m edges are added, if m edges are added, so this is just if one edge is added, all k degree nodes, what is the probability that all k degree nodes change to k plus 1 degree nodes? Because this is the probability which shows that all k degree nodes, the probability that sum of all k degree nodes will receive that edge. This is the value which is showing that sum of all k degree nodes will receive this edge. Okay. So, that essentially means the probability that all these k degree nodes will change to k plus degree nodes if one edge is added. Okay. But if m edges are added, then what will happen? So, this is still less than 1, still this is less than 1. So, one edge is added. So, at most one k degree node can become k plus 1 degree node. Okay. So, I can tell this as probability also, it does not matter. But if I think that m edges are added, then k degree node, all k degree nodes, okay, changing to k plus 1 degree node will be this a k into m, because we think it is independently, the first is coming, these are independent, the first edge is getting added to one k degree node, the second edge is getting added to some other k degree node. So, all the probabilities are independent. Okay. Yeah, we come to this. So, then we have this k plus k 0 p k m plus k 0 into m. Okay. Yeah. So, what you are telling is correct, that there is a subtle assumption here that each edge is falling in different nodes. Each edge is falling in different nodes, which may not be the case which may not be the case. It can so happen that the first edge is falling in node 1 or node 7, the second edge is also falling in node 7. But what is the assumption? The assumption is if m, so m is less than n. So, you are coming with maybe 5 edges, okay, and the number of nodes present in the network now is 10,000. So, if you do some random sampling, it is very unlikely that 2 will fall on the same node. So, that is the assumption, that is why this independence hold. Okay. So, then what happens is I try to put, I put k 0 as 1. So, this will become k plus 1 m plus 1 p k into m. Okay. Is it okay? Okay, very good. So, next we just go on seeing this a little. So, what we have now, n plus p k comma n plus 1 minus n p k comma n. So, what will be added? K minus 1, all k minus 1 all those k minus 1 nodes which are becoming k nodes. This is the addition to this bin, and what is subtracted? So, this is k, sorry, k minus 1 plus 1. Okay. The formula is k plus 1 p k. Okay. So, k minus 1 comma n. I would write it once more, that k minus 1 plus 1 p k minus 1 comma m okay. And again here what we can write, k plus 1 p k comma n into m plus 1. Okay. So, this can be k p k minus 1 comma n minus k plus 1 p k comma n m into m plus 1. Okay. Am I clear? Okay. So, now what is the assumption? Stationary condition. What is the stationary condition? p k n plus 1 is equal to p k n is equal to p k. Okay, this is we have seen through observation. We can prove it also that this equation stabilizes, that mathematically we also can prove, but simply through observation we have seen this is what is happening. So, what does the left side become? N plus 1 into p k minus n p k. So, this becomes p k simply, okay, is equal to k p k minus 1 minus k plus 1 p k m plus 1. Okay. Okay. So, with this I will just write it once more for you. So, k p k minus 1 minus k plus 1 p k m plus 1. Okay. So, let us do a little more manipulation. So, you have m plus 1 if you multiply m plus 1, you can bring m plus 1 here and minus m plus I am trying to bring all the pk's in one point, k plus 1 pk is equal to m k pk minus 1. Okay. So this will become two m plus k plus 1 pk is equal to m k pk minus 1. Okay. So pk is equal to m k sorry 2 m plus m k plus 1 p k. Okay. So I just do some simple, I just do the way. So k plus 2 plus 1 by m p k. Okay. Okay. So immediately we get a recursive regression. And so now let us think what will be for k is equal to 0. What will be for k is equal to 0? So there is a situation where there is a situation where there is a situation where this new node is coming for k is equal to 0, this new node is coming. So for k is equal to 0, what is happening? How many new nodes, how many addition? For k is equal to 0, how many addition? The new node which is coming, that has no in degree, so only one addition. See, you are not adding any other 0 degree node, so only one addition. Only the new degree which is coming has k is equal to 0. It has no in degree. Am I clear? So this is one. Am I clear? Think that the new degree, new node, it is coming with all out degrees, but nobody is still pointing to it. So for k is equal to 0, only one is added, and which is added? The new node. And what are getting subtracted? The same way, if I put this one, okay. So k is equal to 0. Okay, 0 plus 1 is 1, p0 m plus 1, and here what did we have? So we know this will be p0. From this we know this side will become pk, so this will p0, and the right side is 1 addition, and this much is subtraction. Am I with you? The left side, as we have seen, asymptotically becomes pk, while right side we show that just the new node which is coming is added, while what is subtracted is the old nodes with this probability. So this p0 becomes then tell me? I can just take this 2m plus 1 by m plus 1 is equal to 1. Therefore, P 0 is equal to m plus 1 by 2m plus 1. Am I with you? So, this is equation this equations which you have got. Okay, the recursion and the exit conditions.
So, for the first time when it is coming, then we cannot use the previous that our assumption, because that was not.
Yeah, we will talk about initial conditions later, but what we are doing is generalized situation. Okay. So now what we have again, Pk is equal to k plus 2 plus 1 by m, Pk minus 1 and m plus 1 2m plus 1. Okay, I would again make this 1 plus 1 by m into 2 plus 1 by m for k greater than equal to 1, for k is equal to 0. Clear? So, now simple manipulation, we see that Pk is equal to k minus 1, okay, up till it will go 1, k plus 2 plus 1 by m, then k plus 1 plus 1 by m, and it will go up till 3 plus 1 by m into P 0. Okay. Just you can see that it goes on this recursion, and this again we can write as k minus 1 1 k plus 2 plus 1 by m up till 2 plus 1 by m, because this is 2 plus 1 by m, and a 1 by 1 by m stays. Okay. So now you know what is this gamma function. What is gamma A? Or gamma A plus 1, let us, I am sorry, let us write what is gamma A plus 1, A into gamma A. Okay. Gamma A plus 1 is A into gamma A. It shows some sort of factorial behavior. Okay. It shows some sort of factorial behavior, but it A need not be a integer. Okay. It shows some sort of factorial behavior, but A need not be an integer. So, now can you see the above one becomes gamma k plus 1. Okay. Now, let us think this way. So, okay, 1 by m stays outside, forget this. Think this can, what will be the next value of this? 1 plus 1 by m. The next value of this will be 1 plus 1 by m. Okay. So, this will go on for infinity, and above one also will go on for infinity. So, then the what is the below one, tell me? Gamma k plus 2 plus 1 by m plus 1, and the above one is this part, gamma 1 plus 1 by m plus 1. And 1 plus 1 by m stays outside. Am I with you? Okay. So think this. So, we have gamma k plus 1, then you have gamma 2 plus 1 by m, and you have what, gamma k plus 1 plus okay. It is okay. So, what is this? This is gamma A, this is gamma B, and this is gamma A plus B, where okay, this I am just carrying on this, where A is equal to k plus 1 and B is equal to 2. Okay, clear? Okay. So, what is this function, tell me? This is a beta function. So, this is beta A comma B. Okay. So, this is a beta function. Okay. So, now tell me, so how does the, how does the beta function behave for large A and fixed B? Okay, how does the beta function behave for large A and fixed B? Okay. So, anyway, it behaves as a to the power minus b. So, this can be written approximately as a to the power b 1 by 1 plus m. Okay. And that actually becomes what? What is a? K plus 1. So, into 2 plus 1 by, this is m, sorry, 1 by m. Okay. And since A is large, since A is large, what happens? K plus 1 is approximately equal to k. So, then see what can this be written? I put this as a constant, okay, C into k 2 plus 1 by m. Okay. K is large. Sure. Yeah, sure. That minus has to be there. Thank you. Okay. So, what is this now? Huh? This is a power law. So, immediately you see with such a simple model you arrive at a power law. So, this is the power law. Okay. And it is seen that most real life networks, means the more important thing is most real life networks. So, what can be the value of m? So, what will be the value of what will be the range? What will be the range? No, what can be the simplest value of m? The least value of m? 1. Then this value becomes? So, let us write, just let us analyze that. Pk is equal to C k to the power minus 2 1 plus m. So, least value of m is 1, then this becomes C k to the power minus 3. Okay. And largest value of m? infinity, then this becomes c k to the power minus 2. So, what is happening is, it is seen that most real life networks has exponent between 2 and 3. So, this is also noticed that most real life networks exponent is actually between 2 and 3. So, this piece of work not only showed that real world exists, but it also showed that this model can map real life networks where the value mostly vary between 2 and 3. Okay. So, this is upon directed networks, but then Barabasi came in 1998 and simplified these things, and he showed a similar but a simplified model on undirected graph, which we will do in the next class. Thank you.